Often, heat transfer occurs as a combination of the methods we've discussed. For example, fire heats a frying pan by convection. The heat is then transferred from one side of the frying pan to the other by conduction. The egg in the pan is cooked by conduction heating. Steam is complex. When we break down its properties and begin to understand them, we become closer to using the power of steam wisely. In thermodynamic analysis, pressure is expressed in pounds per square inch above a perfect vacuum. This is called absolute pressure and is abbreviated PSIA. Steam pressure is usually measured in gauge pressure. The units are pounds per square inch gauge, or PSIG. It is a measure of pressure above atmosphere, at sea level. Below atmospheric pressure, steam is measured in inches of mercury vacuum. As steam pressure increases, so does the temperature, but by smaller and smaller increments as the pressure rises. There is a corresponding temperature for saturated steam for any given pressure. It is this fixed relationship between pressure and temperature that allows for precise temperature control in steam systems. Rising pressure in the system has an inhibiting effect on molecular movement. When water is subjected to higher pressures, more heat energy must be applied, and therefore higher temperatures must be reached before it can undergo the process of vaporization. As steam pressure increases, so does the heat of the saturated liquid. The amount of heat required to raise the temperature of a pound of water from 32 degrees Fahrenheit to the boiling point at a given pressure and temperature. It is expressed in BTU, British Thermal Unit, or kJ/kg. This occurs for the same reasons that the steam temperature rises with pressure. Again, the heat of the saturated liquid increases as the steam pressure increases. As steam pressure increases, the latent heat of the steam decreases. The amount of decrease diminishes as the pressure rises. Since it is the latent heat available for heat transfer that provides steam's greatest utility for non-temperature dependent processes, it should be apparent that lower pressure systems are most suitable for those applications. The decrease in latent heat occurs because there is a physical limit to the amount of heat that water can absorb in any state. As the amount of heat that is used to raise the water temperature before vaporization can take place increases, the amount of latent heat used to accomplish that vaporization must decrease. At approximately 3,206 psia, the amount of latent heat in the steam drops to 0 BTU per pound. 3,206 psia is the critical pressure for water. At that pressure, it absorbs the maximum amount of heat while in the water state and requires no more heat to turn it into a gas. At this pressure, water can exist either as a liquid or a gas at the same temperature. Add the figures for the heat of the saturated liquid and the latent heat together, and the sum is the total heat of the steam. The total heat of the steam increases with the system pressure up to approximately 435 psig. Therefore, the total heat decreases with increasing pressure. As the steam system approaches the critical pressure, little expansion can take place. The amount of latent heat added to vaporize the water begins to decrease rapidly to increase in sensible heat needed to bring the water to boiling temperature. This results in a decrease in the amount of total heat in the system as the pressure approaches critical for water. The amount of heat available from any medium in its current state is referred to as enthalpy. From steam, the enthalpy of the vapor is the same as the total heat of the steam. This is the sum of the enthalpy of the liquid, heat of the saturated liquid, and the enthalpy of vaporization. Differences in density are generally referred to by the measurement of specific volume. The unit of measure for a specific volume in cubic feet per pound, cubic meters per kilogram. As pressure increases in the system, the specific volume of the liquid rises marginally. Water is incompressible and therefore is not affected by steam pressure. As pressure increases, however, so does the steam temperature. This temperature increase results in greater motion in the molecules of the water and a slight increase in its specific volume. The specific volume of steam decreases as the system pressure increases. At atmospheric pressure, a pound of steam occupies about 1,600 times the volume of a pound of condensate. As pressure increases in the system, the specific volume of the steam decreases. Because of this principle, a greater quantity of steam is available in a smaller space, pipe, heat exchanger, at higher pressures. This is why steam is often distributed at higher pressure but is reduced to a lower pressure to perform specific heat transfer functions. Rising pressure constrains the molecules from moving apart when water vaporizes. At the critical pressure of 3,206.2 psia, the specific volumes of liquid and gas are equal. All of the properties of steam we have reviewed are interrelated. From any one known value, you can determine any of the others. These relationships are all displayed on a table called the properties of saturated steam, or simply the steam tables. For a given pressure, you can read the steam temperature, the heat of the saturated liquid, the latent heat of the steam, the total heat of the steam, the specific volume of the saturated liquid, and the specific volume of saturated steam. The following measurements are expressed in imperial values. If you know that you need a temperature of 307 degrees Fahrenheit, the table tells you that you need to pressurize the system to 60 psig. If you have a 15 psi steam supply, the tables tell you that you have 945 BTU per pound of heat energy available to do work. In this course, we learned steam and identified what steam is, learned how the energy of steam is used, and identified the many properties of steam.